So now we come to the third term, independent events. We've looked at mutually exclusive events, complementary events, and now independent events. So we'll see how that differs from the other two terms. The definition of independent events is that two events are independent if the probability of one event does not affect the probability of the other, or the other way around. So the probabilities do not interfere with each other in any way. And this is always true for mutually exclusive events. And now we have to use the notation for the conditional. So the probability of event A, given that event B occurs. When we talk about this in relation to independence, it means that, well, if we know that B has already happened, does that change the probability of A? And if it does, then we have dependence rather than independence. We'll look at some examples in a Venn diagram. So again, we have this class of 18 students where you have 7 students who study arts, and then you have 9 students who study biology, and 6 students who study neither. So the question is, are A and B independent events, or are they dependent? And the way we check that is to see if the probability of one influences the probability of the other. Now, if these events are independent, we would be able to write that the probability of A is the same as the probability of A given that B happens. So this is what we want to investigate here. So the probability of A is the number of elements in A divided by the number of elements in the universal set, which is 7 divided by 18. Now, the next part can be tricky for some students, the conditional probability. So what is the probability of A given that B happens? And how do we find that? Now, one strategy that I find useful here would be to pretend that set B is the universal set. So if you have a conditional probability given B, what is the probability of A? We pretend that this is the universal set. So out of these 9, how many are A's? Out of these 9s, how many are A's? So out of all the B's, how many are A's? And the portion that we're looking at is actually the intersection, so we could write it like this. So out of all the B's, how many are in the intersection between A and B? And the answer would be 4 out of those 9. And now we can simply check, is this the same as this? And the easiest way to do that is to expand this fraction here, make it into 18ths. So this is 8 18ths. And we can see that, well, okay, this is not the same as this. So the probability of A is not the same as the conditional probability here. And our conclusion then must be that A and B are not independent events. So the probability of A depends on the probability of B. We'll do the same check for these two events in this example. So probability of A is that the same as the probability of A given that B happens? So the probability of A is 3 out of 19, because that's the number of elements in B divided by the number of elements in the universal set. The probability of A given B. Okay, if B happens, what's the probability of A? So if we're here, we know that B occurs. So we have these 10 students. What is the probability that one of these are also an A, an art student? And the answer would have to be 0. Yeah? That there are 0 art students among those 10 biology students. So that's a probability of 0. I think I did make the mistake earlier of saying that mutually exclusive events are always independent. And that's obviously wrong then. Last example today, we have two sets A and B. Is the probability of A the same or different from the conditional probability of A given B? And we find the probability of A first. So this is number of elements in A, that's 8, divided by the number of elements in the universal set, which is 24, which is the same as 1/3. The conditional probability, we pretend that set B is the universal set, and how many elements in set B? That's 15. Out of these 15, how many are also in A? And we would have to look at the intersection. So that's 5. And 5/15 is 1/3. And what do you know? We have the same number. So in this case, this is actually true. The probability of A is the same as the conditional probability. So even though these have an intersection, the intersection is not empty. So these are not mutually exclusive events, but they are independent events. And the reason for that is the probability of one event does not change the probability of the other. We could go the other way as well to just check, double check. Okay, the probability of B is 15 out of 24. And the conditional probability, conditional probability of B, given that event A happens. So we pretend that A is the universal set. We have 8 elements. And how many of these are also B's? Well, 5. And if I multiply with 3 on both sides, up and down, we get 15 24s. So this probability is also the same. So A and B are independent events.